So again, thank you really much for the organizing committee for giving me the opportunity of speaking today about the research activities that we are conducting at the University of Turin regarding the synthesis and characterization of hydrides for energy storage. So as we highlighted today, hydrogen is in the middle of a new enthusiasm wave. And of course, hydrogen can be one of the solutions to fence the climate change. So we need to put great attention to reduce emission. We need to enhance the rapid growth of renewable source, and hydrogen can be a really great energy vector that can move also to a wider range of policy objectives. So for this reason, we know that the cycle of renewable hydrogen is including renewable energies to use electrolysis of water to produce hydrogen in a green way. And during this cycle, of course, the key point is the storage of hydrogen that nowadays can be performed in the liquid, solid, or gas phase. Once hydrogen is stored, we can use hydrogen in a fuel cell to produce again energy wherever and whenever is needed. And having as a waste just water that can close, of course, the cycle. On the other hand, we can also use the hydrogen in the carbon cycle to produce synthetic fuel. In our research group, we are focusing on the solid state of hydrogen storage. That's because mainly in the solid state, hydrogen can be stored in a really safe way and in a compact way. So with low weight and low volume, small volume, we can store a great amount of hydrogen. And this can be done with complex hydride, which are inorganic material that can goes up to 18% of percentage of weight of hydrogen stored in the case of borohydride. So as shown in the figure, lithium borohydride can reach this high gravimetric capacity. On the other hand, the gravimetric capacity of metal hydride, which are alloys that can store in a solid solution or by bonding hydrogen, so forming hydrogen, is lower, but it's still really good from the volumetric point of view. So as in the case of titanium iron, they can reach up to 1.8 weight%. In our research, we are also focusing on the characterization of this material from the thermodynamic point of view. This is because in the literature, there's still a lack of thermodynamic data on this compound, and there's a need of a full evaluation of thermodynamic property and also to understand better the mechanism of hydrogen release and uptake, and also phase stability in all temperature, pressure, and composition range. In order to tailor this material from a compositional point of view, or also by mixing them and enhancing kinetics and both thermodynamic of hydrogen release reduction. So we collect some recent research in these two review that I propose in the slide. And I will show you today some results regarding the characterization of this material, both from the experimental and the theoretical point of view. So our approach is to basically perform a thermodynamic assessment that includes the collection of thermodynamic data, both from the literature, but also by synthesizing new material and investigating the material by calorimetry or by X-ray diffraction and spectroscopy, and also combining ab initio calculation. Once we collect all the thermodynamic data, we perform an assessment. So we try to model the Gibbs free energy of the different phases and structure and compound by a parametric description of the Gibbs free energy as a function of temperature, pressure, and composition. By this assessment, we can build up a thermodynamic databases using the CALFAD approach. So by the CALFAD approach, we can do a phase diagram calculation using this thermodynamic database developed, and also equilibrium calculation that allow us to calculate and compare this data with the experiment we have collected in the literature. So we are closing this cycle, and we are also able to extrapolate information towards more complex system. Regarding complex hydride, the result I will show you today started, of course, to the description of unary and pure compounds. So as in the case of lithium borohydride, sodium, and potassium, we published in the last year the thermodynamic databases of this pure compound. Some assessments were still missing for potassium borohydride, but as you can see in the graph, basically we describe the phase diagram as a function of pressure and temperature of lithium borohydride and sodium borohydride. And this allowed us to understand the phase stability and also the hydrogen evolution mechanism and reaction involved in different pressure and temperature range. Furthermore, we extend the investigation to binary system. So as an example, I will show you this phase diagram developed and assessed in the lithium borohydride, sodium borohydride system. With the CALFAD approach, we were able to collect new experimental data using DSC or in situ synchrotron radiation, X-ray diffraction, understanding the phase stability from an experimental point of view. After all, we collected this data and assessed using a parametric description of the Gibbs free energy of the liquid phase, of the cubic, orthorhombic, and hexagonal phase, which are related to this phase diagram. So as you can see in the slide, we were able to describe with a parametric description, so defining interaction parameter and defining the Gibbs free energy in all temperature and composition range. Once we describe the binary lithium sodium, we moved and we perform also an optimization of the other binary system, so sodium potassium and lithium potassium. And then we were able to extrapolate and use our thermodynamic database to calculate also phase stabilities in the ternary system. And what we observed was the formation of a ternary eutectic with a really low melting temperature, as low as 103 degrees C. And we were able to define well the composition of this ternary eutectic, which in the literature was already proposed, but it was not really the good composition. So by extrapolating and also by new experiments, we were able to define this temperature. And by introducing a negative interaction parameter in the description of the Gibbs free energy, we were able to extrapolate the liquidus temperature evidence in green and find the right composition of this eutectic. So as a preliminary conclusion for complex hydride, we were able to see that borohydrides have really high hydrogen contents and tunable thermodynamics. The thermodynamics of the complex system, binary and up to ternary, can be experimentally investigated and also modeled. And hydrogen release that I didn't show in this short presentation, but I can say that occurs from liquid phase in eutectic mixture at lower temperature than pure compounds. So this was an enhancement of hydrogen release in this kind of compound. However, still we require harsh conditions for reversibility in complex hydride. And that's why we also moved our research to metal hydride, and in particular intermetallic compound, as for example titanium iron, that has been selected for the HyCare project. In the HyCare project, we have a European partnership, both academia and industry, that try to develop an integrated plant to store 50 kilovolt hydrogen in the solid state using iron titanium compound. And coupling this solid state storage with phase change material to improve the thermal management of the plant and also to improve the efficiency and have a low footprint of the entire system. And of course, extending the use of renewable energy by hydrogen. In the HyCare system and in the HyCare project, we synthesize new iron titanium substituted materials, including by alloying manganese and also copper. And what we observe in the graph reported above is that if we determine the pressure composition isotherm by volumetric methods, we can observe that the capacity of the compound can go up to 1.8 weight%, and we can basically tune the pressure of hydrogen absorption and release by playing with the composition. So in titanium-rich alloys, we can enhance storage capacity, but also we can increase cell parameter by substituting iron with titanium, manganese, or copper. And this causes the lowering of the plateau pressure, so we can store hydrogen at lower and milder condition. And the first graph is reported and the study has been recently published, while in the second scheme, we can observe that by elemental mapping in the titanium, iron, and manganese ternary system, we can play with the composition that lead us to also determine a variable thermodynamics of the system. So the enthalpy of hydrogen release can variate with the composition and of course with the alloying we are introducing, the elements we are introducing. So to conclude, we demonstrate that experimental and computational technique are really powerful tools for a complete description of the thermodynamic of the both complex hydride, but also can be exploited to determine the description of intermetallic compounds. We develop thermodynamic databases of complex hydride. We tune also by mixing and chemical alloy the hydrogen release of the properties and characteristic of these compounds. And we demonstrate that low melting mixture of complex hydride can be reached at really low temperature. On the other hand, for intermetallic compound, we reach in iron titanium substituted material a low pressure and temperature hydrogen storage that can be performed up to 25 bar and at room temperature. And that's really an advantage for a large scale application. So to conclude, I want to acknowledge, of course, my group at the University of Turin, all the collaborators at the Aarhus University and also at the Helmut Zentrum Gestes, and of course the iCare Consortium, and all of you for the kind attention. Thank you.